How many people know about quantum physics? Yeah. So I was looking at this. This talk synopsis, and I'm like, maybe this is going to be a good talk.
Maybe not.
Maybe it won't. I guess I won't really know until I take a look at the talk. Yeah? Learned that from a baby book. Yeah, awesome. All right, so let's give Andreas a big round of applause for coming all the way to Vegas from Sydney, Australia to talk to us about quantum cryptography. Have a good time, man.
Thank you very much. All right, welcome everybody. After that introduction, hopefully you walk away and learn something in this talk. So, quantum computing, if you read whatever is in the press, you either think we are completely doomed and the internet's going to end, or nothing's going to happen because they will never exist. So I thought I want to explore this topic a little bit more from an algorithmic point of view and really see where we are, not so much on the hype, but more really what are the algorithms that we talk about right now. So I started various companies in the security space, starting in 2002. Which makes me feel slightly old right now. But first I'm speaking at DEFCON, I'm very happy about this, long-term attendee, but never spoke here, so let's get right into this. So when you talk about cryptography, we mainly look into two different types of cryptography. One is a symmetric crypto system, which is a symmetric shared key, kind of like AES, for example, both sides encrypt and talk to each other with the same key. And we have asymmetric crypto systems which use public key infrastructure, where basically I use a public key to encrypt a message and a private key to decrypt it. There's various forms of this, obviously for digital signatures as well. And in this realm, virtually every crypto system right now that is deployed anywhere is what we call computationally secure. That is secure in the sense that there are known algorithms that can break them. But all of the algorithms that can break them are not easy to do in the sense that, if I want to break an, 2048 RSA key with a normal computer, it takes me a couple trillion years, which means I'm secure even though there's known algorithms that can break them. There are information theoretic algorithms out there, most notably an algorithm called a one-time pad or Vernam ciphers. But they're really tricky and not really practically usable. For example, with one-time pad, you do need to use the same amount of keys as you want to transmit. So if you want to transmit a 1 megabyte file, you need to have a 1 megabyte key. Basically for every byte you need a different, for every byte data you need a 1 byte key. So you would have to manage massive amount of key material, which is not really practically, but I mean, they do exist. But outside of this, virtually every crypto system is just computationally secure. And when you look at this quantum realm, and I'm going into quite some detail about this, for those two different types of algorithms, it is much more interesting to look at the asymmetric part of the crypto systems. Because in the symmetric part, there is a quantum algorithm as well, called Grover, which basically looks into or provides a quadratic speedup to the classical version. Basically in the classical world, if I want to look for this shared key, I need to basically brute force every different combination, which obviously takes forever. I get a squared speed up in the quantum version, which is a fantastic speed up. If I can speed up 150 trillion years, it's a lot of years, but it's still obviously 150 trillion years to break it. So that's not really too interesting. So we want to focus here on the asymmetric part, where the speed ups that quantum computers can provide are massive. And we want to go into quite some detail why their speed up is so big as it is and how they work. So let's revisit just a little bit of how RSA encryption works, and it's really just a basic introduction so we can use them to understand how the quantum versions of these algorithms works. Basically, I choose two prime numbers, P and Q, and with those I just multiply them, get the number n. Now with the number n, I can calculate this lambda n function, which is a Carmichael function, which is just the function. I can easily calculate this. And once I have this, I just choose another parameter e, which is smaller than the lambda n value. And then this n, together with the number e, is my public key. I can give this to everybody out there who I want to choose to do the asymmetric encryption. and I basically retain my private key, which is this number D here, which is just the modular inverse of the number E, which is the public key. Obviously, mod lambda n is always mod lambda n kind of in this scenario, which is the private key that I retain. And with this private key now, with this scenario, I can now look into, hey, I can now encrypt something and send something from Alice to Bob. And as everybody knows, with asymmetric encryption, I can only encrypt something that is smaller than my key. So if I have a 2048-bit key, I can only encrypt something that is smaller than 2048. So I need to pad my plain text into a number n. So I turn this big M into a small number m. There's various ways for this. I don't go into too much detail, but this is where the padding scheme comes in. And then I basically end up with this number small m. And my ciphertext, my encrypted version is really, I just take this number m to the power of e, mod n, and that's basically my ciphertext. And this is what I encrypt with the public key, and I can now send this number C to Bob, or receive this, and if you have the private key, you can easily decrypt this as well on the other side. And you can easily see how this works. It's really very straightforward. If someone has the C and the ciphertext and the D, the private key, by definition C is m to the power of E. So you see, but the definition of D was that it's actually the inverse of E. So this E to the power of D just equals out. So I end up with M mod N. So if I have the private key, I can easily recover the small m. And obviously by just reversing the padding scheme, I have now my message again. So this is basically how RSA encryption works into some detail. So my task is now, I do have a public key because that's public. Everybody knows what the public key is. How do I turn this into a private key? Now, from the definitions, it's really pretty straightforward and simple. I need to find those prime numbers that make up this number n. The number n is known, it's part of the public key. And if I can do this, I can easily calculate lambda n, which is really just the least common multiplier of lambda p and lambda q. And from that I can easily derive the private key d, and I'm done. So all I need to do to basically go from a public key to a private key is to find those two prime factors p and q that I chose in the very beginning when I set up my key, and then I have everything I need to do to basically derive a private key from a public key. While that sounds pretty easy and straightforward, actually to do this and to factor this number n into the two prime parts p and q is really, really hard. And all of the classically known algorithms are all from exponential complexity, which means they are really, really hard to solve. Even, the GNFS algorithm is slightly sub-exponential, but still massive in scale. So that gives you those assurance that if you use any of the asymmetric algorithms, people would need trillions of years to decrypt them, so they're fairly secure for generations to come. But in 1984, a guy called Peter Shor, he was a theoretical physicist, came up with this algorithm. If we were to use quantum computers, obviously in 1984 there was all just a theory, quantum computers didn't exist, and they hardly exist today, but the theory says he came up with an algorithm of how to factor those numbers in just polynomial time. And in just polynomial time really is a difference that is almost incomprehensible. Because it really means instead of taking 1 trillion years on a classical computer with 1 trillion operations per second, let's suppose I have a quantum computer which just does 1 million operations per second. I can actually do the same thing in just 10 seconds. So the difference between exponential complexity and polynomial complexity is just out of this world. And that obviously, if we could run this algorithm, would pose a big threat to basically the whole crypto systems as it is deployed. Because the base of this, whether it is for RSA or elliptic curves, or for digital signatures, ECDSA, which is used in Bitcoin, or for key exchange like Diffie-Hellman, which is mainly used in everywhere you go on SSL, TLS exchanges. So the base foundation of this is used virtually everywhere in today's internet. So that would be a big threat. So let's explore a little bit how Peter Shor could come up with his algorithms, what is actually needed, and how they work in reality. So now we need to do a little bit of an introduction into quantum computing, and it gets only as deep as I thought we need to go to understand how Shor's algorithm works and what we need to understand. So hopefully it's not too bad. So basically there are two big types of quantum computers that we look at right now. One is called gate-based quantum computers. That's a big chunk what everybody's working on. All the big guys, IBM, Intel, Microsoft, Alibaba, they're all working on gate-based quantum computing, which is called universal quantum computing, because I can solve virtually any problem similar to a classical computing on this computer. There's a different computer called quantum annealers or adiabatic quantum computing, which is what's the first quantum computer that was available was from D-Wave. And D-Wave's computer, this adiabatic quantum computer, is not a general quantum computer. You cannot solve every problem on this quantum computer. It is very specialized to only solve a particular optimization problem. So it's very much, you can look at this basically as a physical system, and physical systems tend to always end up in the lowest energy state, which we call the ground state of this physical system. So if I can now define a function that I want to solve, and I basically define those functions in a way that the lowest energy state is basically the same as the solution to this optimization problem, I can use this physical system to solve the problem that I have, because I know the physical system will end up in the lowest energy state, in the ground state, and I know then this also represents in the state where my optimization problem reached the lowest point. And there's a really cool theorem which actually guarantees to me that I end up in the lowest state that there is. You can really think of this as kind of like mountains and valleys, and you can end up in a valley that is just halfway through and you're not really in the lowest state. But there's a theorem, we are going to explore this a little bit, which gives me way how I can really be at the lowest state so I can solve, or I can find the optimal solution to this optimization problem. But it's really just solving optimization problems. The gate-based quantum computing is really a general computing architecture where you start with an input, you apply all sorts of different calculations to it. Technically, those are all gate-based calculations. You do an AND gate, you take 2 qubits, do something to it, you get a result. But essentially, you have an input, you calculate something, and you have an output. And it's basically, you can calculate everything you want to calculate with these universal quantum computers, while quantum computers like D-Wave can really only solve optimization problems. But actually, as it turns out, both approaches can be used to solve the factorization problem. And we have Shor's algorithm from 1994, which uses gates to solve this problem. And in quantum annealing, we have various approaches since 2002, and I want to explore those a little bit in the next couple of slides as well, how they work to actually solve the factoring problem as an optimization problem. So let's dive a little bit into quantum computing and what I need to understand to explore a little bit Shor's algorithm, and really with the idea of giving you an understanding of how can someone derive an algorithm that gives me now such a dramatic improvement over a classical algorithm which takes exponential time to solve. So the basic building blocks for quantum computers are what we call qubits. Qubits is the equivalent of a classical bit. A classical bit is either 0 or 1. A qubit is now you can almost think of it as a quantum mechanical system which can be in any state you want it to be, and you don't actually really know in what state it is. But once you measure this quantum mechanical system, it is either going to be 0 or 1. And this is something that we're going to exploit later on, that before we measure this system, we don't know in which state it is, but it can be actually in a superposition, it can be in a state where all of these qubits can interact with each other, and only at the very end of my processing step, I will measure the system, and all of those superposition states will basically terminate, and I know it's either 0 or 1. But it's really a quantum mechanical system. You don't really know what it is. It's neither 0, it's neither 1. It is something in between. Quite often we then assign variables to it, and here you can see a representation of one of those qubits. We have these two bases, 0 and 1, which basically represent this 0 means if I measure this particular qubit in 100% of the cases, I will get the measurement outcome of 0. The 1 means in 100% of the case of measurement, it will give me the measurement outcome of 1. And now a qubit is in the superposition of those two with alpha and beta. Those are two complex numbers. I can represent those, and that can now define the state of this particular qubit. Now, we call alpha and beta probability amplitudes, because if I measure this particular qubit, I will now get the probability of the measurement outcome to get the measurement outcome 0, the probability is going to be alpha squared, and the probability of getting the measurement outcome of 1, it's going to be beta squared. Remember, when I measure this particular thing, even though I have two complex numbers associated with it, when I measure it, it's going to be either 0 or 1 with a certain probability associated with it, and the probabilities are really defined by those two numbers, and basically to the squared for alpha and beta. I know it's going to end up in 0, and with those two numbers I can represent those qubits. It's basically a mathematical representation of the quantum mechanical system that the quantum computers operate in. But remember, all of these measurements and everything we do in the quantum world is probabilistic. Everything is just a probability. I can put a quantum in a state where I can tell you in exactly half of my measurement it's going to be 0, in half of my measurement it's going to be 1, which is perfect for random numbers, for example, because I can tell you, hey, you don't really know whether it's 0 or 1, it's exactly equal probability of getting 0 and 1, so I just take one qubit, measure it 5 trillion times, and I get 5 trillion random bits. But obviously, I don't really know whether I get 0 or 1, it's all defined by probabilities, which has a big implication on the algorithms, because the algorithms will also only give me probabilities. There's no algorithm that can give me, I run through this algorithm once, and it will give me the answer, yes, it is this answer. It will always only give me, yeah, I think with 83% probability it's going to be this answer, for example. So quite often you run these algorithms multiple times to really see where you end up with. The second principle that we need for Shor's algorithm is the concept of entanglement. And that gets slightly philosophical. I want to focus a little bit more on the mathematical part of this. Entanglement is basically a property where I can have two qubits, and I know that there's some correlation between those two qubits. In a classical world, I have two bits, and the two bits are completely independent of each other. Neither of those bits will interact with the other. And if this bit is 1, doesn't matter what this is. In a quantum world, I can have a relationship, a correlation between those two qubits. And a simple example is this Bell state of two qubits. So this state is here a state where you have two qubits. In those funny notations, the first 0 is the value of the first qubit, the second 0 is the value of the second qubit. But if I would measure this qubit here, and let's suppose I measure the first qubit as being 0, it cannot be the second one because the first qubit was 0. So the second qubit has to be 0 as well. I know that the second qubit is going to be 0 simply because I measure the first qubit, and there's no way, because I don't have 0 1s or 1 0 in there, that the second qubit could something different than 0. So I take basically two qubits, give them into this quantum mechanical system, prepare this Bell state, and now I have two qubits that are separate from each other, but in this quantum mechanical system, those qubits are now correlated, or what we call entangled. And now I could give one qubit to Alice and send her to the moon, and one qubit to Bob and send him to Mars. And I know that if Alice looks at her qubit and Alice says, oh, I got a 0, I know Bob has a 0 as well. Even though there's no communication between those, simply because there's this correlation, those properties. Now, I need obviously those two qubits, I need to prepare them together, and then I can send them anywhere I want. And they are correlated without any communication in between those two. There's lots of philosophical implications because I could put those two qubits light years away from each other, and did I really find a way of communicating faster than light? No, I didn't, because if Alice measures, it's going to be 0. If she wants to tell Bob, hey, I measured 0, she needs to communicate this information to Bob, which obviously she needs a few light years to do so. But it's an important principle that we're going to use in Shor's algorithm as well. And the main thing for you to understand is the exponential large size I can look into when dealing with those quantum systems. Let's suppose I take 2 classical bits. I can represent 4 possible states with 2 classical bits, but only one of them at a time. So, you know, if you see the 4 states there. My system with those 2 bits is in one of those states at any point in time. In a quantum world, I can take 2 qubits, and basically at the end, when I measure this system, it's also going to be in one of those 4 states. But before I measure this system, because of superposition, those qubits can be in all 4 states at the same time. And only when I measure the system will collapse to one of those 4 states. And this is exactly now a situation we're going to exploit, where if I have n qubits, I can represent 2 to the power of n states. While I do calculations, I still at the end of the day need to know what the result is of my calculation. So I need to measure at some stage, and then it will collapse obviously to those n states. But during calculation, I have 2 to the power of n states, which is a massive amount of states that I can represent with just a few amount of qubits. So now I have everything kind of to look into Shor's algorithm and how it works. And we're going to look into this. So the main idea that Shor had was actually, if I want to look into how to factor n into p and q into those 2 prime numbers, I don't actually need to solve that problem. That problem is equivalent to a different problem. And basically he looked into number sequences, and he realized from number theory that you have a number sequence. For example, you look at a number sequence here, you multiply the previous number by 2. So if 1, 2, 4, 8, 16, 32. If you now use this number sequence and do this mod 15, for example, in this example, you end up with a number sequence 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8. This is what we call a periodic sequence. So it's always going to be the same kind of sequence of 1, 2, 4, 8. And we can now define a number which is called the period, which is 4, which is basically the number of the amount of numbers before it repeats itself. And the underlying algorithm from Shor is that if I want to find out the factors for this number n, if I want to find out this p and q, I can actually transform this into a problem of finding the period r. And that turns out, for that problem, I can run this very easily on a quantum computer. So basically, if I look into this, and the cool thing is, and I want to show you this on the next slide, the mathematics behind it is actually fairly trivial. A basic level of linear algebra gives you everything to understand how this works. So the only thing you need to accept is that out of number theory, there's a theorem which basically says this function fa, x to the power of I mod n, is a periodic function if x has particular properties. And now I only need to find the number, the period r. And with this, I have my algorithm Shor, which we run through in quite some detail actually, but essentially it's comprised of 3 phases. First is I turn this factoring problem into a period finding problem, and that's actually trivial. Then I use a quantum computer to actually give me this period r. To solve this period r on a classic computer is again really, really hard. Actually, on a classic computer is still of exponential complexity, which means that this algorithm on a classic computer does not give me any advantages whatsoever. But I can use a quantum Fourier transform, and that gives me the speed up. And then basically once I have the period r, I can really very trivially use this to find the factor. So step 1 and step 3 are really trivial. Step 2 is where all the magic happens, and that's where the that's where the main speed up comes. Now I don't want to go into too much detail, but it's actually really simple. So I think you can download the slides and you can look through this. I know that fa is periodic. I know that x to the power of 0 is 1. I mean, everything to the power of 0 is 1. And if r is now my period, I know, because the function is periodic, that x to the power of r mod n equals 1, 2, equals the same what it was before, because it is period. And really, with basic linear algebra, I can now use the x to the power of r equals x to the power of r half to the power of 2. And I can just write this in a different form, which gives me this multiplication of two numbers that will give 0 mod n. So if I can use this, if I have this r, I have these two numbers. So, but if those two numbers mod n is those are an integer multiple of n, because their product is 0 mod n. So that means they're an integer multiple of n. So either those are directly factors, or if they're not directly factors, each one of those has a factor in common with the number I want to look at. So the greatest common divisor, which is actually not too hard to compute classically, it's just an n squared complexity. So by computing the greatest common divisor for each of those numbers with n, I have my factors for n. And that is really simple, but to get to this r is really, really hard. But I can put this together in a really quick example. Let's suppose I have n equals 15. Now everybody can calculate in their head that the prime numbers are 3 and 5. Basically, I choose any integer between 1 and 15. And let's really use, for the sake of simplicity, let's use x equals 2. So you can see my period here, mod 15, is 1, 2, 4, 8. So I have the period 4. I can see this. That's a really hard part to calculate. But with the period 4, the greatest common divisor of x to the power of r half is r is 4, so r half is 2. X is 2, so that's 2 to the power of 2, which is 4. So the greatest common divisor of 3 and 15 and 5 and 15, so 4 minus 1 and 4 plus 1 is obviously 3 and 5. And when you calculate this through, actually in every case you come up with 3 and 5. So that's exactly what Shor's algorithm is all about. But the really hard part is figuring out what is this period r. And this is kind of where the quantum algorithm comes in. And those quantum computers or those quantum algorithms always work in the same principle. You basically, you initialize basically the result that you want to see and say, let's think of, we want to get a 256-bit number or 2048-bit number. And you basically, every bit of this bit representation is going to be either 0 or 1. So you basically put this in an equal superposition. So every bit you basically put at 50% 0 and 50% 1, because you don't really know what it is. So it's really kind of like at 50%. Then you run through this quantum Fourier transform, which will use amplitude amplification. So with every iteration of this algorithm, those amplitudes will now go towards 1 or to 0, which is going to be the final result. And you run this through a number of times, and then you measure it at the end, and you will see when you end up with. I'm going to have an example of this when we run this through on a real quantum computer. But just to summarize, Shor's algorithm altogether is fairly simple. You choose any random number a, which is smaller than n. You compute the greatest common divisor. If this is not 1, actually you found a factor and you're done. But that's obviously not, most likely not the case. I use my quantum computer to find this period r. And once I have r, I just need to find the greatest common divisor of those two terms, and I'm done. So another example, I choose randomly number 7, calculate period r equals 4. I have this greatest common divisor of 48 and 15, and 50 and 15 gives me 3 and 5. So it all works fine. I can now use this and use a library, a toolkit called QuizKit, which is an open source toolkit. There's now at least 5 or 6 different open source platforms how you can use quantum computers and how you can program quantum computers, either on quantum simulators or on real quantum hardware. And I gave you some references here. You can look up those. It's actually kind of fairly easy to go through. But they all start the same. And here you see an example of this amplitude amplification. Basically, in the end, you see all of the possibilities what my prime numbers could be. they're all in the same probability what they could be. That's my starting point. And once I run through this algorithm, and I ran through this Shor's algorithm from these references, the amplitude of the correct results have now been amplified, and the amplitudes of the wrong results have now been kind of like gone down to 0. And I actually see that there's two results, r equals 0 and r equals 4. R equals 0 is obviously trivial probability, so I discard this. And I end up with r equals 4. So this was now executed on a quantum simulator. Quantum simulator, I can simulate a quantum state on my normal computer. But remember, in quantum computing, we're exploiting this fact that I have this massive large space of 2 to the power of n. So I'm going to have really trouble simulating more than whatever 100 qubits or so on a normal computer. And, but for smaller ones, for illustration, it's actually quite cool. So the cool thing is IBM has a quantum computer that you can publicly access. You can write a quantum computer program, execute it towards their cloud. It's very simple. You just change, hey, my backend is the simulator. You change the backend to IBM's quantum computer. And if you execute this against a real quantum computer, it's just a 5-qubit quantum computer right now, I still get r equals 4 with the highest probability. But you see there's lots of other probabilities. And those probabilities are representative of all the errors you have in the system, simply because those quantum computers that we have right now are really pretty bad. They are what we call noisy. They don't produce the correct results. Because they're noisy, they produce lots of wrong results. Now by repeating my algorithm lots of times, I can still get around this fact. And obviously in this case, I still have r equals 4, the highest probability. But obviously that has big implication on performance because I need to now repeat these algorithms much more. And obviously I will end up in dead cases because obviously the noise will basically reduce the speed up in the quantum effects to 0, and it basically collapses to a classical computation that I have. But the cool thing is actually with Qiskit as well, there is libraries for every quantum algorithm that that people know, and they kind of provide easy libraries. If you want to run Shor's algorithm to factor any numbers, you just import Shor's algorithm from Qiskit Aqua, which is a library. You just say, all right, I want to factor this number n equals 15. I use a simulator. I do this 1,000 times, and off I run this instance, and I get a result. How cool is that you can run this against a quantum computer? And the only thing you need to do in this example is if you run this against a real quantum computer is to change this backend from the simulator to a different backend. And now there's a call out to IBM's quantum computer to run this on their backend. It's actually really, really cool. And this feeling when you run a quantum computing software for the first time is actually quite cool. So I encourage everybody to look at Qiskit or various quantum computing libraries and to play around with this. So the problem obviously is, and you guessed it, that in order to do anything meaningful, I need lots of qubits. So in order to use Shor's algorithm to break RSA 2048, I need 4,000 qubits. And I need 4,000 proper qubits, meaning without any noise. I need for the time of the computation, there can't be any noise on the computation as well. And it's not really a surprise because when Shor came up with this in 1984, there were no quantum computers. He didn't have to worry about, hey, can I really implement my algorithm or not? He really just came up with a system and method. So it was never really meant to run on a quantum computer. And right now, lots of people look at Shor's algorithm and then say, all right, kind of right now we have 70 qubit, so it's the qubit count doubles every year, whatever, so it's going to be another 10 years before we have Shor's algorithm. Nobody's going to run Shor's algorithm because it was just a theory. So let's look at some of the researches where people took Shor's algorithm and modified them and optimized them to run on real quantum hardware. So the first one was Fowler in 2012. Basically, the first approach was really kind of, I need to tweak this algorithm so it can sustain errors. Because Shor's algorithm really was on the assumption there's no errors, all the qubits are fantastic, no errors. So basically they used what's called the surface codes to allow for errors to occur, and the error rate is 0.1% of the gate error rate. And Fowler came up, I can run Shor's algorithm and I can factor 2048-bit number, but I need 1 billion qubits to do so, which is obviously a massive amount in terms of overhead to run this. So that was in 2012, not too long ago. And then in 2017, with further optimizations from O'Gorman, we suddenly kind of like had an algorithm where we reduce this 1 billion qubits to just 230 million qubits in 2017. And those are really optimizations in the physical connectivity of those qubits. And then Giorgio kind of reduces further to 170 million qubits. So you can see there's algorithmic improvements without any hardware improvements, obviously that's happening at the same time as well. But obviously I get down from 1 billion qubits to right now 170 million qubits. And the biggest contribution was from Gidney and Akira from Google and University in Stockholm, where they provided a paper just not long ago, earlier this year, where they looked into how they could do the same thing what everybody else is doing with just 20 million qubits. Now, we went in 2012 from 1 billion qubits to 2019 to 20 million qubits. And we are far from the end of the research there in terms of optimization to this problem. Now, I won't go into too much detail of this, of what they do, but basically they also look into lots of optimization of how things work. And they basically also choose, similar to Shor, not really look into factoring the numbers directly. So they basically convert this factoring problem into short discrete algorithm problem. And they have a part that is computed classically and a part that is computed quantumly on a quantum computer. And they can show that in order to find P and Q, they can come up with, obviously they know what N is, which is the multiplication of those two. They can come up with a number where they know the addition of those numbers are D, so D is known. So if they have two equations for two variables, which they can fairly easily solve. Fairly easily is obviously an overstatement because they still need 20 million qubits to do so. But obviously the reduction from 1 billion qubits to 20 million qubits is massive. And I expect in the next couple of years there's going to be lots of optimization to Shor's algorithm, and especially to Gidney and Akira's algorithm, where this is going to be reduced further on. Obviously 20 million qubits is still a long way away from quantum computers that are accessible today, where we are in the realm of, slowly below 100 qubits at this point in time. So I want to spend the next, or the last 10 minutes of my presentation on approaching quantum annealing. Those is the second type of quantum computer, and that is actually what's quite surprising to me, even though everybody's talking about Shor and the implication for cryptography. Actually, quantum annealing right now is much, much further ahead in terms of solving this factorization problem, and we're going to look into a little bit how these algorithms work. So as mentioned before, quantum annealing, those computers are really computers where it can solve an optimization problem. I need to define my problem as an optimization problem. And then basically quantum annealing computer can take this problem and find the minimum of this problem because it represents a physical state, and I know the physical state will always end up in the ground state, and I can read then this ground state and I have the solution to my problem. And there's really a cool theorem where you want to go into the lowest point. You want to find this lowest point on the right-hand side. So how do we end up in this lowest point and not get caught up in those minimas in between? And there's lots of ways how you can do this from the physical system. And there's a really cool case on this quantum annealing case where there is a theorem that says if I start in a very easy quantum mechanical system, in this really easy quantum mechanical system, I know the ground state. So this is my problem I want to solve is here. I am starting here and I really know where I am. I can now slowly evolve, and adiabatic means slowly evolving the state from this here to the state where I really want to be. And now this theorem gives me a guarantee or physical proof that I will end up in the maximum or in the optimal minima of the problem I want to solve. And it's really cool. So I have Hamiltonians are functions that define a physical system. But basically, if you look at the first function, if you put in s equals 0, you end up in this h0, which is my easy to understand system where I know the local minima. And in my calculation, I slowly move S from 0 to 1. And if I'm at 1, I'm in a stage H1, which is the problem that I really want to solve. But this adiabatic theorem guarantees to me that I will end up in the maximum minima for the problem that I really want to solve, which is really, really cool because it gives me, I know I'm not going to be caught into some local minima. But still, essentially, I want to solve an optimization problem. How do I do this? And the first research came from Burgess in 2002 from Microsoft, where, you know, he provided a foundation of, hey, I want to solve, basically if I want to look into the problem n equals p times q, I'm looking for p and q so that this equation is true. So I just need to solve this, I need to write this as an optimization problem. And basically he rewrote this as n minus pq squared. And this is a positive function, this is always greater than 0, and this is obviously only 0 if n equals pq. And if you write it this way, you have what's called a QBO, a quadratic unconstrained binary optimization problem, which you can happily run on any quantum annealer that is out there. And you basically use binary representation, and it's really just a fancy way up here of writing pi and qi are just the ith, you know, bit, it's either 0 or 1. And you basically now write this down, and it's a very simple example. My example 15 is 5 times 3. Now in binary notation, p equals x1, 1. The last bit always has to be 1 because the prime number can't be an even number. And I just, you know, n minus pq squared, I just write this through and kind of by hand and see, oh, this is a function I need to minimize now. And I can run this against D-Wave's quantum computer, and if I find the minimum, I know n equals pq, because that's by definition a positive function. So I can use Quantum's, D-Wave's quantum computer, they provide a library as well. And you see the link here, you can download it. It's basically the same thing, I just call factor p, p is my product, and I can run this on this D-Wave's quantum computer. The problem is, if I just use this without any optimization, I need n squared qubits for this. So I mean, my number of qubits that I need really kind of like grow quite heavily, and for larger numbers this is not sustainable to do. But I wanted to show you it's all probabilistic, so if I run this one time, I end up with my 415 for the p and q for my 2 prime numbers is 1 and 7, which is obviously wrong. So I ran this once, and I didn't really end up in the right spot. But I ran this 5 times. Now I've already have 5 and 3 is already 60% you know, probabilities. And if I ran this 50 times, you know, I know my prime numbers are 3 and 5. So I need to run those quantum algorithms more and more often to make sure I end up in the same results. I'm going to skip over some of those things because virtually all optimizations of now this base, you know, of Burgess's work, where he basically looked into, hey, my multiplication matrix that you write out as a function to be minimized, there can be lots of optimizations. Virtually all of the work that I will present here now is based on optimizations of how you do the multiplications down below here. If you've ever done multiplications by hand, you know, you start on the right and you kind of multiply the lowest numbers, and then you have carryovers to the left, and virtually all of those optimizations go through this, how I can do these multiplications much easier. Dridi and Agassi did some work in 2016 where they used some of these optimizations to remove some of the order of the degrees. So they were already able to factor a number greater than 200,000 with almost 900 qubits. Now D-Wave's qubits on quantum annealing are don't have to be as good as universal quantum computer qubits. So D-Wave announced a system with I think around 5,000 qubits for next year. So 900 qubits was what available back then. On universal quantum computers, the biggest prime number is less than 100. And these guys in 2016 could already now factor a number that was over 200,000. The big breakthrough was from Zhang in Indiana in April 2018, and it's really kind of mind-blowing. You see the next one, which was really just 2 months after, really around optimization of this multiplication map. And they've now they could factor a number which is greater than 350,000 with just 94 qubits. Remember, DWAVE comes up with 5,000 qubit quantum computer next year. And it's all based on this optimization problem that we solve for factoring and with the optimization to the multiplication table. And then Peng in earlier this year really, and you can see this submission was received in July, while the previous submission was, I think, submitted in April or something like this, just months after. Optimizes even further, and they've been able to factor a number that is greater 1 million with just 90 qubits. So that's already 20-bit number. So right now, when we look into the problem of, hey, can I use a quantum computer to factor prime numbers? Universal quantum computers and Shor's algorithms are nowhere compared to quantum annealers. And with quantum annealers, I can already do this with 20-bit numbers. So there's three things really interesting. So they could run this on already existing hardware today. And all of those algorithms, and that's a really big takeaway that you have. To do this, I don't have just one quantum problem that I want to solve. It's always a hybrid model of some classical computation and some quantum computation. I really use a classical computer, what he's good at, and a quantum computer, what a quantum computer is good at. So my point is, quantum annealers are 1,000-fold better right now than Shor's algorithm on universal quantum computers. But because they are too noisy right now, we are far away from breaking anything that is used in practical terms. Right now, the biggest number is a 20-bit number. But obviously, we know those two kind of like converging curves here. The algorithms are getting better and better. At the same time, the quantum hardware gives me more and more qubits as well. So both of them will actually have a big impact. I can't just rely on my prediction saying, hey, the number of qubits grow by 50% every year, so I'm going to be fine for the next 50 years. You're neglecting the improvements that the algorithms will make over the next couple of years too. So a couple of myth and reality. Shor, nobody's going to implement Shor on any quantum computer whatsoever. Shor was a theoretical work. There are practical work, derivations of this work that will be implemented. At some point, obviously, on the basis of Shor's algorithms, people will break the RSA encryption. It is a matter of time. Now we can argue whether it's 10 years, 20 years, 50 years, but we're only arguing about the time. We're not arguing about that it will happen. And obviously there's lots of cases where this is already has an impact right now. If I have bitcoins right now and if my public key is known, I don't care whether it takes me 20 years to get the private key to those bitcoins. If I'm getting 20 years, there's 1.5 million bitcoins from Satoshi flying around, which is around $12 billion right now. Hey, if someone comes to me and says, hey, Andreas, can you build me a quantum computer? I said, hey, it's really hard. It takes me $12 billion. Hey, here's $12 billion right there. So. So anyway, it will be quite a while, but I want to provide an overview of the algorithms. I started this talk talking about just the asymmetric world of the RSA world, but there's plenty of work, and this is kind of from this Chinese paper in the very end. That's their end statement. There's plenty of work underway right now to use quantum annealers, also to look into symmetric encryption. So if you say, hey, I just use symmetric encryption, I'm fine, that may not be holding up for too long. And I thank you very much. I'm out of time. Thank you very much for your time. Do we have time for questions? We don't have time for questions. You can find me anywhere if you have some questions. Happy to engage with you. Thanks very much.